Alright, hey everybody. As we start working through these equilibrium problems, there'll be some times where there'll be a pulley involved with the problem. So I want to do a quick review on what a pulley is and how we deal with these pulleys within these equilibrium problems. So as a review, if I had to define what a pulley is, what a pulley does is it will change the direction but not the magnitude of a force. So as an example, or a couple short little examples, if I had some kind of box and it was being how do I want to draw this thing? Let's like this here, some kind of pulley. Let's say I have a rope that's going up along this pulley and I'm pulling down on it. If this box had a weight of 100 pounds and I were pulling with some force P and I wanted to know what that force is, I could draw a free body diagram of this box, and what's going on here is this pulley is changing the direction but not the magnitude of that force. So the direction as it leaves the box also has to be 100 pounds, and as it doesn't change as it moves around from my equilibrium equation, sum of the forces y equals 0, I know P is equal to 100 pounds. About the easiest way you'd see a pulley. If we bump it up a level, draw a better box than that. If we were to bump it up a level and instead had a pulley that was attached, let's see how I want to do this. Let's draw two pulleys. It's actually one pulley problem. And let's attach the pulley to the top cog. It's going to go down, around, up, and over, something like that, right? And I'm going to pull with some force P. And once again, this is going to be a 100-pound box. If I were to look at the free body diagram of what's going on with this box, I still am supporting this 100 pounds. And with this pulley, now I know the tension in the pulley has to be the same wherever I am within the pulley. Well, this pulley has two different forces that are pulling up. Each one have to have the same magnitude P, or the tension in the cable, right? Or two T's in this case, what I'm doing for tension. If I look at this free body diagram from my sum of the forces in the y equals 0, I can see that that tension then would be equal to 50 pounds, half the total load. And you can do this as many times as you want. What you're really looking at is your anytime you have any kind of direction change, I know that the force in the pulley has to be the same throughout. Need to focus on how I'm drawing this last one. This one, I'm saying if I had a pulley, looks like that, and I'm going to attach it at the bottom, it's going to go up and around and then down the outside and then up and then come down here with some force P. I'm still supporting this 100 pounds. Take a second and see if you can come up with what the overall force P that I'd have to apply in order to lift this box. Got it in your head? So looking at the free body diagram, I have this 100 pounds pulling down, going up. What I have are three tensions, each one of these being T, T, and T. So what I would end up with is that this force P, or the tension in the cable, I guess I should be doing P in each one of these, right? P would be equal to 100 over 3 pounds. I guess P and T are in essence the same thing, but be consistent. All right, so let's look at a real example. Let's say that I have a crate of some sort down here, and I know the mass of the crate is 200 kilograms. I'm supporting this crate with a couple of cables that are coming up here, and that is going to be attached to some kind of pulley wheel. I'm going to have a separate pulley that's attached to the ceiling, so put about here, and let me attach that to the ceiling, make it look a little more reasonable. Off to the side, And the way this is going to work is it's attached to the center of this pulley. It's going to go up, around, down, and then pulled up with some force P. And this has to happen at some angle alpha. So let me give you some dimensions so we know what we're talking about. We're going to say that at this point in time, my distance between the pulley, the one pulley and the other pulley, is 2.4 meters. Oh, this definitely is not drawn to scale. Let me move this out of the way too. And the distance from one pulley over to the other pulley horizontally is 0.75 meters. So what we are asked to find in this case are two things. We're looking for both the force P and this angle alpha in order for this crate to be in equilibrium. So here's the key to this problem. I know that the tension is the same anywhere within this cable. Alright, so if we look at, let's start by looking at what weight we're supporting. I know weight is equal to mass times gravity. We have a 200 kilogram crate. Multiplying that times our 9.81 meters per second squared gives me something like 1962 newtons. So that's our force or support we're supporting. If I were to look at a free body diagram of the situation, I'm going to put my dot, my representation, right on that pulley wheel, because from that pulley wheel what I see is that the weight of the crate, the 1962 newtons, is straight down, and then I have a force from each one of the cables, or each portion of this cable that's pulling around these pulleys. So I have the force that I'm pulling up with this P, and that's at this angle alpha away from the horizontal, and that same force P has to be pulling up twice on this other side. So these are both P and P, and I could find out the angle that these things are acting because I'm given some dimensions of 0.75 and 2.4, and if I found the hypotenuse for those two, I get something like 2.51, and both those P's, even though they don't quite look like it, should be the same angle. So from this, from my sum of the forces in the x direction equals 0, because I know it's in equilibrium, it is not moving, I have my P in the positive direction times the cosine of this alpha minus these other two P's, and then their angle in the x direction would be their x component over that hypotenuse of 2.51 is equal to 0. So I could move the negative side to the other and divide through by p's, and I see my p's actually go away. The only thing I'm left with is an alpha for an unknown. So cosine alpha must equal 2 times this 0.75 over 2.51. Solve that for alpha, and I end up with alpha is equal to 53.3 degrees. For the second part of this problem, I'm going back into statics, and I'm saying sum of the forces in the y direction equals 0. I have these two p's on the one side, and then their vertical distance is 2.4 over this hypotenuse distance of 2.51. Plus, also pulling up as this other single force on the right hand side times the sine of my new angle that I just found, 53.3 degrees, minus this 1962 newtons that's pulling it down, must be equal to 0. From that I can solve for P. It's my only unknown. I end up with P is equal to 723 newtons. So that's kind of how you deal with these pulleys. You realize that the pulley is causing a change in direction but not magnitude. If you have a single cable that's going around different pulley wheels, always, wherever you're cutting it or whatever you're doing with it, always make sure you have the same magnitude. Hope that was helpful, and I look forward to talking to you all soon. Thanks.